Welcome to iLecture Online, and here we're going to explore inductance. And we're going to look at mutual and self-inductance. Now, mutual inductance is the inductance between two coils. Self-inductance is the inductance caused by one coil on itself. So the problem here says we have two coils, so we're dealing with mutual inductance. And the two coils have a mutual inductance of 0.55 times 10 to the minus 3 henries. If the current in the first coil is increasing at 250 amps per second, what will be the induced EMF in the second coil? So to understand this a little bit better, let's draw a couple of coils. So here's coil number 1, and here's coil number 2. And if current flows through each coil, so let's say we have a current flowing through coil 1, which is I1, we have a current in the second coil, let's call it I2. And it says that the current in the first coil is increasing at 250 amps per second. So the I1 dt, the change in the current of the first coil per unit time, is equal to 250 amps per second. Now, before the coil, let's say before the current in coil 1 changes, imagine that there's a magnetic field in coil 1 that goes through coil 1 that also goes through coil 2. So if there's a current in coil 1, there will be a magnetic field through the coil which will also go through coil number 2. And so the mutual inductance between the two coils can be defined that M is equal to the number of turns in, let's say, coil number 2 times the flux going through coil number 2 divided by the current of coil number 1. So that's the mutual inductance. But they already told us what the mutual inductance is, so we don't have to calculate it. The second thing we need to know is that if the current changes in coil number 1, it will cause the flux to change in coil number 2. And of course, we've learned that if the flux changes through a coil, it will induce an EMF. The EMF induced in the second coil is equal to the mutual inductance, or I should say the negative of the mutual inductance between the coils, times the rate of change of the current in the first coil. So that's di1 dt. So since we're given the mutual inductance, and we're also given the rate of change of the current in coil number 1 as a function of time, we can say that this is equal to minus the mutual inductance of 0.550 times 10 to the minus 3 henries. And my bracket needs to include the negative sign, so there we go, times the rate of change of the current, which is right here, which is 250 amps per second. 250 amps per second. And let's see, do I have my calculator? Right here. Okay, what is it equal to? So we have 0.550 e to the 3 minus times 250 equals, so that would produce or induce an EMF, a voltage, of minus 0.1375 volts. So henries times amps per second is the same as volts. And there you go. So that's how we calculate the EMF induced in a second coil when there's a mutual inductance between the coils, and we know how fast the current is changing in the first coil, and we know the extent of the mutual inductance between the two coils. And that's fairly straightforward at that point.